Welcome everyone. In this video, we are going to continue our work with for loops. I want to talk about nested for loops, which is when we have a for loop inside of another for loop, which could be inside of another for loop. And we'll take a look at a context of where this might be useful to apply. And it's going to be back in that k nearest neighbors type of problem. So what we would do when we're nesting for loops is I have an outer loop here, which has an iterator I. So we're going to iterate I over some range of values or strings in a vector. And then we start that for loop. And then we might have some code. And then at some point, we start another loop inside of that using a different iterator. So maybe J inside of a possibly different vector. And then we could have some code, and then we could have another for loop inside of there where we use a different iterator like k and enter some code, and we could embed more and more loops inside of there. So this code above has 3 loops. The outer loop is iterating over I, the second loop over j, and then the innermost loop is over the iterator k. So the innermost loop is going to run the fastest, k, since it just has to go through itself. The second loop, in this case j, is going to take the second longest to run because for each value of j, we need to run through the full loop of k. And then the outer loop I is going to take the longest to run because for each value of I, we need to run through each value of j, which then needs to run through each value of k. Okay, so as you're writing these nested loops, I will just say that the spacing, the line breaks, and the indentation convention that we've been doing gets more and more important. It makes the code more and more readable. So each time you have another less nested for loop, you want to indent all of the commands related to that for loop at another indentation level. Okay, so we're going to take a look at the nearest neighbors, and we're going to have nested for loop. So just to keep the situation a little more digestible, let's just take a much, much smaller data set than the nearest neighbors data set that we had before, or excuse me, than the iris data set that we had before. So I'm just going to create a matrix called chords. And let's just imagine I have a data set of 5 values, and we record the x and y values. You can think about these as like coordinates in a plane. One point is at 1, 9, one point is at 4, 4, 2, 3, 5, 2, and 3, 1. So for each location in my data set, I want to identify what are the other 3 locations closest to it. So in order to do that, I would need to calculate the distance of my 1, 9 from these 4 other values. So 1, 9 is a distance 0 from itself. How far is it from this one? How far is it from that one, and that one? So we want to calculate the distance. And how we calculate the distance between 2 points in the plane, the most standard way of calculating distance is to use what's called the Euclidean distance, which just takes the difference in x values and squares it, and then adds the square of the difference in y values, and then takes the square root of that sum. So this is what we're going to want to code inside of our nested for loop, is this formula. That's equation number 1 up here. So what I need to do is first I'm going to create kind of a receptacle of where we're going to store all of these distances. So I'm going to call this matrix D, like we named it in the earlier example. And I'm going to define a number of rows and the number of columns, but nothing else. So this is just going to be a blank matrix. It's a container where we can store calculations that we're going to do next. So the number of rows of my matrix is going to equal the number of observations in my data set. So in this case, I have 5 rows, I have 5 collections of points. So here I could have entered 5, but again, I don't want to hard code that. It's a bad habit to get into, so I'm going to calculate the number of rows of my sample. And my matrix is going to be a symmetric square matrix. It's going to have the same number of columns as it has rows. So each row is going to correspond to a single observation. And then across that row, each column is telling me a distance of that point to some other point in our data set. So we're going to store all of these distances in matrix D. Then we're going to create a nested for loop that's going to calculate the distances. So I'm going to need to do this n different times. So I'm going to store the number of observations in my data set, which is the number of rows of this matrix chords. That's the number of observations. So n row chords is equal to 5. That's calculating we have 5 observations. So for each observation I, where I is going from 1 to 5, we're going to then go in, and in this inner loop, we're going to calculate the distance of each of the 5 points from that fixed point. So let's just think about how this loop is going to go at first. It's going to set I equal to 1, and then it's going to go inside this inner loop. And then it's going to pick j equal to 1. So initially it's going to have I is 1 and j is 1. So it's going to calculate the distance of element 1 from itself, which should be 0. Then it's going to go and increase the next value of j. So it's going to keep I set at 1, and it's going to run through all of the values of the inner loop. So first it's going to set j equal to 1. The distance of 1 to 1 is 0. Then it's going to set j equal to 2. And now I want to calculate the distance of element I equals 1 to element j equals 2. So it's going to take the x coordinate, which is located in column 1. So these are the x coordinates of each point. So this is going to take the x coordinate of point 1, which in general might be I, minus the x coordinate of our second point, which we're indexing with j. And it's going to square that distance. It's going to do the same with the y coordinates. So the y coordinates are in column 2. So it's going to take the y coordinate of the ith entry, subtract the y coordinate of the jth entry, square that distance. It's going to add those two differences squared together and then take the square root. So it's implementing this formula right here, where index I is telling us the first point, index j is telling us the second point, and then we're calculating the distance between point I and point j, where I is going from 1 to 5, and j is also going from 1 to 5. So this is going to first set I equal to 1, and then for each of the other 5 points, calculate how far is each of those 5 points from the first point. Then it's going to increase I to 2. And then it's going to run through j going from 1 to 5, where it's going to calculate how far is point 1 to point 2, how far is point 3 to point 2, how far is point 4 to point 2. And it's going to run through all of the indices on the inner loop j. And once it's gone, once j is equal to 5, it's done calculating distances to j, to the original I value, and then it's going to increase the value of I by 1 and move on to the next row. So this is going to fill out our distance matrix row by row by row. I do not think I ran this. Okay, sorry. I don't think I created my matrix D of the right dimensions. So D is a 5 by 5 matrix. And again, this is telling me the first element is distance 0 from itself. This is telling me how far the second point is from the first point, how far is point 3 from point 1, and so on. So again, we get a symmetric matrix with diagonal entries all equal to 0 because each point is distance 0 from itself. And it's symmetric because the distance from point 1 to point 2 equals the distance of point 2 to point 1. So now we've calculated all of these distances, and we can compare that to the distance function, which is built into R, and just double check that our calculations worked, and we're getting the same matrix back. So this is exactly how that distance built-in function dist works in R. It's just running a nested loop similar to the one that we just coded up here. Okay, so that is a wrap on for loops. We'll take a look at while loops next.